In this chapter, we will start to apply some of the concepts of inferential statistics in order to conduct a hypothesis test. In our scenario, we have been tasked with assisting a vacuum store. Each vacuum they sell comes with the offer for a warranty. And there are two different options for the warranty length, a 5-year and a 7-year. We want to know which warranty, when offered with the purchase of a vacuum, drives more revenue per customer. To do this, we need to generate some samples to compare and analyze. We cannot capture this information for the entire population, so we will need to make inferences from our samples. So, let's assume we have observed the vacuum store for 2 weeks. We have collected data for 3 samples. The first sample contains customers who were not offered a warranty. The second sample contains customers who were offered the 5-year full warranty. And for our third sample, this contains customers who were offered the 7-year limited warranty. Each sample contains 750 visitors to the store. After these 2 weeks are over and we've collected our data, we now have the mean revenue per customer for each sample. We start by comparing the sample means of the 5-year and 7-year warranties. When we compare the two means, we can see that the 7-year limited warranty has a revenue per visitor that's about $7 higher. So we have a winner, right? Well, maybe not. This is where we can run a hypothesis test. We will calculate the p-value for this scenario to measure the significance of the differences that we're seeing between the two samples. And we can use this p-value measure to conclude whether the differences occur by chance or occur because of an underlying effect. As we explored earlier, we will also need to determine the confidence level of our hypothesis test in order to generate our alpha, which we will need in order to interpret our p-value. Finally, we will need to interpret the results of our hypothesis test. Does our p-value indicate that we can reject the idea that these two samples are the same? Or do we fail to reject this hypothesis? In the following lessons, we will review each of the steps in our hypothesis test in more detail. Through this scenario, we will see how inferential statistics can help us in the real world by running a hypothesis test. Let's get started. Here is the data that we've collected to run our hypothesis test. Before we jump into conducting our tests, let's go through some descriptive statistics for us to explore and familiarize ourselves with our data. We can start by generating a list of descriptive statistics from the data analysis add-in. Let's select this order value column, and we can go to the data tab on the ribbon and data analysis. We can select descriptive statistics, hit OK. Our input range is this order value column. We do have labels in our first row, and let's output the data in cell F1. Make sure that we check the box Summary Statistics and hit OK. These descriptive statistics already give us a sense of the entire dataset. We can see that the mean value is $53, yet the median and the mode are both $0, indicating no sale. If we check out the range, we see the order value ranges from $0 to $1,300. And just by looking at the first few rows of our dataset in the Excel workbook here, we can see a lot of 0 values. Ideally, I want to see some of these stats, like total revenue and revenue per visitor, broken down by each sample group. And we can do that just underneath here using some Excel formulas. So we want to calculate the total revenue as well as the revenue per visitor. So we can use the unique function to return a list of unique values for our different samples. And now we can use some additional Excel formulas to return the sum of the order value for our total revenue and the average order value, or the revenue per visitor, for each of our sample groups. So we can use a SUMIFS function for this. The range that we want to sum is our order value. our criteria range is our sample group, and our criteria are the different samples here. Now we can see the total revenue for each of our sample groups. So we see that the 5-year full and the 7-year limited both have a higher total revenue than offering no warranty at all. We can also break this down by revenue per visitor. So let's copy this formula across, and this time we can change the sum to an average. And let's format all of these as currency as well. Now we can see the revenue per visitor for each of our 3 samples. Once again, the 7-year limited warranty has the highest average, followed by the 5-year full, and then offering no warranty. Now that we've seen our descriptive summary statistics, as well as some statistics broken down by our different samples, let's create a histogram of this order value column to get a better understanding of the distribution of the revenue. So let's select our order value column, and we can insert a histogram. And let's resize this over here. So as expected, we see a lot of 0 values, but right now this histogram is a little bit too granular, that we can't really get a better understanding of the distribution of our data. So let's double click on the axis, and let's change the bin width, instead of 45 to be 200. And we can start getting a better sense of our data. We see a lot of values between 0 and 200, between 2 and 4, 4 and 6, 6 and 8, and then maybe some smaller values over to the right here. We know we have a lot of 0 values, so let's select and create an underflow bin. And we'll set this value to be 1. So every value less than 1 has its own bin, and we can start to see the distribution of our actual sales in the middle. We'll do the same thing for an overflow bin. Let's set this to be 1000. And now that we've changed the bin sizes, let's add some data labels so we can see exactly how many rows from our data set are in each bin. So as we knew before, we have mostly 0 values indicating no sale. But now we can see that actually the most common sales occur between the range of $400 and $600. We have sales between $200 and $400 as well, and on the higher side between $6 and $8, and a handful of potentially outliers at over $1,000. Now that we have a greater insight into our dataset, we can move forward with our hypothesis test. Okay, now that we're more familiar with our data, we can start going through our hypothesis test from start to finish. There are 5 steps to do this. First, we need to state our hypothesis, and we'll state both a null hypothesis as well as an alternative hypothesis. Then, we're going to state our significance level. Third, we'll need to select our statistical test. And then fourth, we'll apply our test and calculate a p-value. Finally, we'll draw a conclusion about our null hypothesis. The next few lessons we'll walk through and explain each of the steps using our warranty scenario. Our first step is to state the hypothesis that we want to test. And there are actually 2 hypotheses that we need to state: the null hypothesis and the alternative hypothesis. Identifying our null hypothesis is simple. The null hypothesis is always that there is no difference, and it is often represented by H0. In our example, the null hypothesis would be that there is no difference between the 5-year and 7-year warranty. The mean revenue per visitor when displaying a 5-year full warranty is the same as when we display a 7-year limited warranty. The alternative hypothesis, represented by HA, takes the opposite stance. In our example, the alternate hypothesis would be that a 7-year warranty is not the same as a 5-year warranty in how they drive revenue per visitor. As we discussed earlier in the course, our test will either reject the null hypothesis or fail to reject the null hypothesis. We will never say that the null hypothesis was proven correct. And this is because an experiment can never prove the null hypothesis is true unless we test the entire population. If our results reject the null hypothesis, we can then say that they support the alternative hypothesis. In some scenarios, the alternative hypothesis might be worded slightly differently. Rather than testing two things being different from one another, we may want to take a side and state that one will be greater than the other, as an example. We will cover a scenario like this later on in the chapter. Now that we have our null hypothesis and alternative hypothesis, we can set our confidence level. Our confidence level sets the probability of correctly failing to reject the null hypothesis, assuming that the null hypothesis is true. Using our example, assuming the effects of our two warranties are the same, then the confidence level is the chance that our test would conclude that they are the same. A popular confidence level is 95%. So, when the null hypothesis is true, we have a 19 in 20 chance of concluding that there is not a statistically significant difference between our two warranties. If we lower our confidence level to 90%, there would be a greater chance of a false conclusion. However, this greater uncertainty can allow us to work with a smaller sample, which could save us time and money. So selecting our confidence level is a trade-off, depending on how important the accuracy of our results is. In our scenario, we don't have to worry about these constraints, so we'll stay with the 95% confidence level. For our calculations later, we'll also need to have an alpha value. Recall that the alpha value is 1 minus the confidence level. Our confidence level in this case is 0.95, so our alpha is 0.05. Now our third step is to pick the statistical test we will use for our analysis. We will review two of the most common types of tests, a two-tailed test and a one-tailed test. Using our example, a two-tailed test will test to see if there is any difference between our two warranties. The two-tailed test gets its name because we're rejecting the null hypothesis if it falls on either of our tails. Let's review the following visual to see how this test relates to our stated hypothesis and the confidence level and alpha that we selected. Here we see a distribution of our samples. The area in the middle is our confidence interval. It contains 95% of all expected samples. 95% of the time, we'd expect our results to fall within the confidence interval, assuming the null hypothesis is true. The areas colored in orange each contain 2.5% of all expected samples. Together, they contain 5% of all expected samples. If you recall, 5% is our alpha value. If our sample falls outside of the middle section, in other words, outside of the confidence level in the orange area, then the probability of our samples being different due to pure randomness is low. This would only start to happen about 5% of the time. So, if our result falls outside the confidence interval, we'll reject the null hypothesis and conclude the difference is more than randomness. If it falls within our confidence interval, we fail to reject the null hypothesis. In addition to the two-tailed test, there is a one-tailed test. With the one-tailed test, we only reject the null hypothesis if it falls to a specific side, which we state in our alternative hypothesis. This test is suitable if our alternative hypothesis states that one specific warranty was better than the other, as opposed to simply stating that there is a difference between them. If we take a look at our visual again, notice how our alpha is only visualized on one end of the distribution now. We can only reject the null hypothesis if our result falls within this one specific area. In our example, we didn't state a preference for either warranty in our alternative hypothesis, so this test isn't appropriate at the moment, but we will come back to this later in the chapter. For now, we will apply a two-tailed test for our hypothesis. This is a good test based on the alternative hypothesis that we selected. With the data from our test, our alpha value, and our statistical test, we can calculate our p-value. Doing this by hand is pretty intensive and rarely done. We'd first find our t-statistic. We'd then need to reference a table or a scientific calculator to get our p-value. Most data scientists would instead use a tool like Python or R to calculate their p-value. We'll explore these tools in some of our other courses, but for this course, we'll be running our test using functions built into Excel. So to start, we need to structure our data for this analysis. Let's go back to our dataset and add filters to the columns. Let's just filter to the 5-year full warranty. And I'm going to take this order value column, copy it, and I'm going to paste it in the first column of the two-tail sheet. I'm going to rename this column to be 5-year. Then back in our data tab, I'm going to do the same thing for the 7-year limited warranty. I'm going to take the order value column and I'll paste it next to the 5-year column and rename it to 7-year. Now I'm going to go to the data tab on the ribbon, back to data analysis, and I'm going to select t-test to sample assuming equal variances. We use equal variance because our sample sizes both have the same number of observations, and we don't have any other reason to assume that the variances would be different for these two samples. If one of our two datasets was larger, or we knew one sample naturally had a different variance, we'd want to use the t-test that assumes unequal variance. As for the paired t-test, we would use that when measuring two variables on the same subject. For example, if we're running a blind taste test with Pepsi versus Coke, then we might want to give each participant both drinks in unmarked cups. When each subject receives both variables, like our Coke and Pepsi example, we use a paired test. For our vacuum warranty example, if we showed potential customers both warranties and let them pick the one they preferred, that would be a good paired test experiment. But since we didn't structure our test that way, we'll go with the t-test to sample assuming equal variance, and we'll hit OK. For our variable 1 range, I'm going to select the 5-year column, and for variable 2, I'll select the 7-year column. Our hypothesized mean difference here is going to be 0. This states our null hypothesis, as we don't think that there's any difference between them. We do have labels, so make sure that this is checked. And our alpha we can leave at 0.05. Finally, for our output, let's go with an output range, and we can put this in cell D1. And hit OK. The output provides us with our mean, the variance per each sample, as well as the pooled variance here, which is an average of our two variances. We'll only see this pooled variance if we ran a t-test assuming equal variance. And finally, what we're really interested in is our p-values down here. Since we're running a two-tail test, the p-value that we want is the lower one, the two-tail p-value. So we've come to the final step in our hypothesis test, drawing our conclusion. To do this, we need to compare our p-value to our alpha. If our p-value is less than or equal to our alpha value, we reject the null hypothesis. Otherwise, if our p-value is greater than our alpha value, we fail to reject the null hypothesis. In this case, our alpha value is 0.05, and our p-value, as we see here, is 0.423. So, we fail to reject our null hypothesis. If the null hypothesis was true, we'd expect values this extreme about 42% of the time. That's fairly common, so I don't feel confident that the differences observed between the means of our samples is significant. Notice that our hypothesis test can only reject the null hypothesis or fail to reject the null hypothesis. We never say, for example, the null hypothesis was proven correct. This is because it can never prove the null hypothesis true unless we test the entire population. So while our sample wasn't able to reject the null hypothesis, it also wasn't able to prove it. The only way we could prove it is by testing the entire population. For our first hypothesis test, we ran a two-tailed test, as we wanted to test to see if there was any difference between our two warranties. Using this type of test, we failed to reject our null hypothesis. We have the option now to run another analysis, this time using a one-tailed test. With the one-tailed test, we only reject the null hypothesis if it falls to a specific side, which we state in our alternative hypothesis. So before we conduct our test, we need to update our hypothesis. A fundamental premise to this entire experiment is that being offered a warranty, any warranty, will sell vacuums better than not being offered a warranty at all. Do our visitors really care about warranties? Does it actually change their buying habits? Well, we have the data to test this. We'll perform another hypothesis test with the sample of 750 visitors who were not offered a warranty. This sample is drawn over the same time period as our other two samples to limit any seasonal bias. Once again, our null hypothesis is that there is no difference. This time, that there is no difference between being offered a 5-year warranty and not being offered a warranty at all. For a one-tailed test, we might state the alternative hypothesis as, we think that the offer of a 5-year warranty is better than an offer of no warranty. After all, that is what we're trying to learn. For this test, we will focus our attention to the left side of our distribution. We'll leave our confidence level at 95%, meaning we'll reject the null hypothesis if our test shows a value less than the leftmost extreme 5%. Since we are only rejecting the null hypothesis if it falls to one side, we will use a one-tailed test. Let's head back into Excel to conduct our second test. For our one-tailed test, let's repeat the same process as before. Let's filter our sample group to the 5-year full, grab the order value column, and copy it to the one-tail sheet this time. I'll paste the values in and rename to 5-year. Back in our data tab, we'll filter our sample group column again, but this time to the none. I'll hit OK, select the order value column, and copy it next to the 5-year. And I'll rename this to none. We'll go to the data tab on the ribbon, data analysis, t-test, two sample assuming equal variance, hit OK. And since we've already run one t-test, or two-tailed test, previously with the same structure, all of our input should already be here, but we can double check just to make sure everything is set up correctly. Our variable 1 is column A, our variable 2 is column B, our hypothesis mean difference remains 0, we have labels, and our alpha is set up. We can output to the same place, D1, so I'm going to hit OK. This time, we want to select the first p-value that says one-tail test up here, and our p-value is 0.022. We also want to check that the mean of our second variable, the no warranty sample, is actually smaller than the 5-year, which it is, 39.6 compared to 56.3. This tells us that our sample falls to the left side, as our alternative hypothesis predicted. Since our p-value is less than our alpha of 0.05, and the no warranty sample is the smaller value, we are going to reject the null hypothesis. We can be confident in our alternative hypothesis that the mean sales of a customer shown a warranty is higher than the mean sales for customers not shown a warranty. Now that doesn't mean the difference is actually $16 or so, but we are confident that there is some difference between these two samples.